Good morning. Actually, it's probably not morning when you are watching this, but it is morning right now. So good morning. Lighting is still a little off. All right, we are in day 3 of solving systems by elimination. If that tells you anything, if you may be struggling, that may tell you that this isn't as easy as I may make it look. I don't know. It's just not as easy as it seems. So please do not get discouraged. All right, so let's find out how multiplying equations by a factor can help us solve systems of linear equations. A little review. Systems of linear equations, they work wonderful when you have what I keep saying, terms. Here's a term, here's a term that have the exact same letters and the exact same numbers in front of the letters, but different signs. So if I add these two equations together, I get 7x, the y's cancel, equals 15. We're going to stop there because I just made this equation up off the top of my head, and it's not going to be a pretty solution. So that's when elimination works. Let's see if I can turn that off. Yeah. All right, now we talked about a little bit last lesson, but how multiplying equations by a factor can help us solve system of linear equations. If we had, say, 2x plus y equals 13 and 5x minus 2y equals 4. Making it up again. Okay, the y terms have opposite signs, but not the same coefficient, not the same number in front of the letters. The x terms have the same signs, but one has a 2, one has a 5. So I can multiply an equation by a number like 2 and get something that will be nicely cancelable, because that's a word. So I just multiplied everything by 2. I just doubled that entire first equation. And that cancels those 2's out now. If we add these together, I get 9x equals 30. Still not going to do anything from there because it's fine. But it doesn't change the equation at all. If I graphed this equation and this equation, I get the same line, the exact same line. Yeah, let's move on. All right, so you have this written in front of you. I made a new slide so that I could work with it, yet, hold on. So I could work with it, but not have to look at this. So here we have x plus 5 equals 11. What is the solution to this equation? Okay, if I subtract 5 from both sides, I get x equals 6. That is the solution to that equation. All right? Hold on. Actually, upon further digging, you don't have this part. Okay? But, well, I'll just read it out. So we're going to do this slide, and it'd be a great idea if you would like to take notes. So here, I've got this equation. So we're going to talk about the solution to this equation. That's step 1. What is the solution? Oh, I pushed a button on my pen again. Let's erase that. The solution to this equation is subtract 5 from both sides. I have x equals 6. Next thing, if we multiply both sides of the equation by a factor, say 4, what equation will we have? So I'm going to multiply the equation by 4. So that gives me 4x plus 20 equals 44. Okay, what's the solution to this one? So we're going to solve it the same way. Subtract 20 from both sides. That gives me 24 equals 4x. Divide both sides by 4. X equals 6. I still got 6 for an answer. Now, what if we multiply both sides by 100? Certainly we won't get the same answer if we multiply both sides by 100. So I have 100x plus 500 equals 110. 1,100, because I can do multiplication. All right, subtract from both sides. I don't like bigger numbers. I get 600 equals 100x. Divide both sides. I have x equals 6. What? We get the same answer? Amazing. All right, so I'm just reminding you that these equations are one variable equations, and that multiplying both sides of a one variable equation by the same factor produces equivalent equations. Okay, no matter what we've done, when we multiply both sides of an equation, we get equivalent. Okay, that's my little reminder because we need that information today. It's very, very important. I did not change the equation. I multiplied by a factor and the equation still gave the same solution, just the one variable equations. Okay? Now into our warm-up. This you have. All right, so use graphing technology to graph the equations. Then identify the coordinates of the solutions. X plus y equals 1, and x plus 2y equals 9. All right, that right there is the coordinates of the solution, -1, 5. Okay, so write that down. That's your solution. Write a few equations that are equivalent to equation A. Let's go back here. So this was -1, 5. All right, write a few equations that are equivalent to equation A. So I see equation A by multiplying both sides by the same number. So, for example, 2, -5, or that should be 1/2. Those fractions don't translate very well sometimes. So if I multiply the whole thing by 2, I get 8x plus 2y equals 2. If I multiply it all by -5, I get -20x minus 5y equals -5. And then equation 3, multiply everything by 1/2. So half of 4 is 2x plus 1/2 y equals 1/2. All right, I'm going to graph these equations. Let me make sure I'm going to turn the page here. Yep, okay. So 8x, this is our first one, plus 2y equals 2. We look, our red equation is now green. See how I'm changing the color? Haven't changed anything. 20x minus 5y equals -5. Thought I got that wrong. I multiplied by -5. Oh, -20. There we go. All right, so our red and our purple have now, sorry, turn it off purple, turn it on purple, red and purple. All right, next one. 2x plus 1/2 y equals 1/2. Okay, red and black are now the same. So we didn't change the equation at all by multiplying the entire equation by a factor. Graph the equations you generated, make a couple of observations. They're all the same. Same graph, same line. How can we explain the identical graphs? Because we multiplied both sides of the equation by a factor, so everything changed equally, so they're equivalent. What move was made to generate A1, A2, and A3? We multiplied by a factor. Why did it create equations that are equivalent to A1? Because in algebra, if you multiply the left side and the right side by the same factor, you're not changing the equation. It looks different, but it's not different, okay? If we created a table with x, y values for each equation, how would the values compare? They would just be bigger. Again, they would all be on the same line, bigger values, if we multiplied by a bigger factor. So I can't say bigger, because we multiplied by half and it got smaller, right? So I can't say bigger. I think we're going to do that. No, we didn't. So if we created tables with x, y values for each, for 4x plus y equals 1, if I just do a really simple table, I get 0, 1, 1, -3, let's just do 3 points, 2, -7. If I do 20x plus 5y equals 5, and I think we had negative 20x, negative 5y equals negative 5, it's equivalent again, xy. If I plug in 0, I get 1. If I plug in 1, I get -3. If I plug in 2, amazingly enough, I get -7. And then try the half. 2x plus 1/2 y equals 1/2. Guess what's going to happen? If I plug in 0, I get 1. If I plug in 1, I get -3. And if I plug in 2, I get -7. All right, our table doesn't change. How can you use what you've learned about isolating a variable to show the equations are equivalent? Here, if I write in red, if I solve this one for y, because it's easier, I can do y equals -4x plus 1. Let's get rid of these negatives. If I do this one, I have 5y equals -20x plus 5. Divide everything by 5. I get y equals -4x plus 1. They're equal. Same for that third equation. Okay, if I isolate the y value, I'm going to get the exact same equation. It's kind of like magic, but it's not. All right, so here's another system that we solved by graphing earlier. So we've already solved it by graphing, but remember, we're practicing today how to solve it by elimination. So to start solving the system, Alina wrote everything right over each other, right? Of course, we changed it. So equation A stayed the same. Equation B changed. And then she wrote this. I don't like how they do that, but it's okay. Okay, 4x minus 4x cancels. So she subtracted them, and the 4x eliminated. And then y minus 8y is -7y. 1 minus 36 is -35. So her first move was multiply equation B by 4, and then subtracted the equation. So complete solving this process algebraically and show the solution. So if I divide both sides by -7, I get y equals 5. Then I plug that back into any equation I see, and I'm going to plug it in. Let's pick this one. X plus 2 times y equals 9. X plus 10 equals 9. Subtract 10 from both sides. And I get x equals -1. Okay? To show the solution is indeed that, I'm going to plug both of those, the ordered pair, the solution, back into any other equation. Let's change colors, see what we're doing. I'm going to plug them back into here and make sure it works. So 4 times -1 plus 5 equals 1. So -4 plus 5 equals 1. 1 equals 1. It does work. So what did I do there? Okay, we have the original equations. Alina multiplied this equation by 4 and plugged it in there. And then she subtracted the equations and then finished the process. Okay, if I graph the original equations, okay, this is equation A, equation B. I have equation A and equation B. Alina's equations, let's see, this is 4B. That right there is equation 4B. 4 times B. So she took equation B and multiplied by 4. So it's still going to graph under B. And then here, equation C, it's another equivalent equation. You can add equations together, subtract equations, and you get another equivalent equation. They all intersect at the ordered pair, -1, 5. So I have 4 equivalent equations written on this screen. Equation A, equation B, 4 times equation B, which is equivalent, and we're going to call this equation C. Equation C was found by subtracting equation A and equation 4B. All right, so writing a new system to solve a given system. I think we're going to pause on this. Well, let's do it. So here are 2 equations in the original system. In solving the system, what do we assume about the x and y values in the equations? They're variables. That's what I assume. Okay. We didn't, so I go here. So equation B1 is really 4 times equation B. We didn't use the original 2 equations to solve. Instead, we multiplied each side of equation B by 4 to get equation B1. How do you know the same xy pair is also a solution to equation B1? We can test it. 4 times -1 plus 8 times 5 equals, let's see, that gives me -4 plus 35, 40, is 36. Okay, so it is a solution because 36 equals 36. Okay, then to get from here to this next step, we subtracted them. So I kept the first equation there, but I subtracted these 2 equations, subtracted them, and I plugged my answer to those subtractions right there. So 4x minus 4x is gone. Y minus 8y is -7y. 1 minus 36 was 35. So this right here is another equivalent equation. How do we know the same xy pair from earlier is also a solution to equation C? Let's plug in our solution. -7 times 5 equals -35. That's true. -35 equals -35. All right. And then solving equation C, dividing both sides by -7, does give us y equals 5. Solving equation C gives us y equals -5. How do we find the x value? Well, I take this y and I can plug it into here. I can plug it into any of the equations that we've seen so far. Okay? I substitute y equals 5 into another equation and solve for x. So if we substitute this pair of values for x and y in equations A, B, B1, and C and evaluate the expressions, what can we expect to find true statements? Yes, and we've tested quite a few of those. We will find true statements. This right here is the solution to the system. All right, let's summarize a little bit. Equivalent systems are systems with the exact same solution set. Our solution set in this equation, or in this system, was -1, 5. Suppose we want to solve the system by first eliminating the y value. What factor would we choose? Well, our original system was 4x plus y equals 1, and x plus 2y equals 9. Suppose we wanted to solve the system first by eliminating the y value, the y variable. Well, I would multiply equation A by 2 and then subtract. I would actually multiply A by -2 and then add, because it'll give me the opposite signs, and I like adding. Could we multiply equation A by 6 and equation B by -3? I don't know. Let's look at it. Here's equation A and equation B. If we multiply equation A by 6 and equation B by -3, I don't know what that is giving us. Let's do it and see. So equation A would be 6 times 4 is 24x plus 6y equals 6, and equation B would be -3x minus 6y equals 27, -27. Yes, if we add these two equations together, the y terms eliminate, and we could continue on and get the same answer. Okay, that's sort of fun. All right, your teacher will give you some slips of paper with systems of equations written on them. Each system represents a step in solving this particular system. Arrange the slips in the order that would lead to a solution. Be prepared to describe what move takes one system to the next. Explain why each system is equivalent to the one before. We're going to do this in class. If you're distance learning, it's okay. You can definitely work through these. They're all here. And email me if you have any questions whatsoever, okay? All right. This right here, hold on. I think that might be my cooldown. Yep, that part is optional. So we will finish here, all right? All right, that's a long lesson. And really you're going to learn the most by practicing yourself. Good job.